Okay, folks. How's the pendulum going? Anybody else balanced at this point? I saw one group that was comfortably balancing the pendulum, and another one where it would kind of teeter for maybe 10 or 15 seconds and then lose it. So it looks like things are coming together. Hopefully with one more week of lab time, we'll see some more balanced pendulums. Any questions about that stuff? Any bugs people would like to talk about? Yeah.
With, what was it? It was like the way that it was reacting, and it turns out our IMU was upside down.
I was going to remind folks of this bug because I've seen it in a few different groups. If you so one of the things that you're plotting in real time on the VGA screen is the complementary filter output. Pay attention to that complementary filter output and hold your pendulum steady, and then move it relatively quickly in one direction or the other direction. And what you expect to see from the output of your complementary filter is that it quickly responds to the new angular position of the arm. If instead it looks like your complementary output sort of goes the other way temporarily and then corrects itself to come back down to the new arm position, that's a good indication that probably your IMU is on upside down, which means you can either take the IMU off and turn it around, or alternatively, you could go into, let me just pull up the demo code for the IMU. Or no, sorry, that's in the complementary. Let me pull up the complementary filter page quick. I just want to show you the one quick correction you can make. So if you find that your IMU is on upside down, you can, here where you compute the accelerometer angle, you can add a minus sign in front, right? And that should fix the problem. Like I said, you'll see the complementary filter output go temporarily the wrong direction and then correct, and it'll kind of feel almost as if your angle is getting low passed or something. Anyway, that's a quick fix that prevents having to take apart your arm mechanically. Any other questions from folks? Is anyone still having noise problems? Sensor that's getting locked up because of motor noise? Or have most people mitigated that at this point? It seems like most are working pretty stably. Okay, sounds good. In that case, my plan for today is to do a bit of a deep dive into some of the demo code that you all started with for this particular lab. This is the PWM demo code that you used in week 1 of lab 3 to set up the open loop control. And the section of code that I want to de-obfuscate a bit, hopefully, is lines 84 to 87 here, where we're setting up the PWM interrupt service routine. We talked previously about interrupts on the RP2040 as sort of a useful level of abstraction for getting things done in the lab, sort of how to set these things up from within the SDK, that sort of thing. What I'd like to do today is do a sort of a deep dive, a couple of levels of abstractions deeper than we've talked about before, about how interrupts are working on the RP2040, which means we're going to take a brief excursion from the RP2040 datasheet into actually the ARM datasheet to talk just a little bit about how the ARM M0s in the RP2040 handle interrupts. Okay, so I want to clarify these lines of code just a little bit. And in order to start that conversation, I'd like to take a look at the data sheet as usual. And in particular, I want to look at the interrupt section here, just to remind you what we're talking about. So if we go to the processor subsystem, the particular subsection based on interrupts, I'll just remind you that this is the table of the 26 interrupts that are shared between the 2 cores on the RP2040. Remember that the RP2040 has 2 cores. You all know this by now. Each of those is an ARM M0, and they share these 26 interrupts. This is the interrupt number, and then next to the number in this table is a brief description of the hardware peripheral that it's attached to. So we can see, for instance, that interrupts 0 through 3 are attached to the timer peripheral. These specifically are usually set and manipulated using those alarm registers that we talked about in the timer peripheral. But if we read this section, what it tells us is that Each core is equipped with a standard ARM nested vectored interrupt controller, an NVIC. So the system that is actually handling these interrupts in the ARMs is this nested vector interrupt controller. And I want to talk just a little bit about that. There is actually a section of the RP2040 datasheet that talks very briefly about this. Let me just show you where that lives. So we can go into the Cortex M0 section, NVIC, and it's a very brief section because this NVIC is an ARM thing as opposed to a Raspberry Pi thing. So the bulk of the information lives in the ARM documentation. And this is largely just what that's telling us. What it says in particular is, if we scroll down a little bit, the interesting thing that I wanted to just point you to is this particular list of registers associated with this NVIC. And I want to look at one in particular, which is this NVIC_ISER, interrupt set enable register. If we look at this register, what this particular register is telling us is which of those 26 interrupts are enabled. So a really interesting experiment that you can go do is, using this data sheet, you know the location in memory of this particular register. It's at an offset of hex E100 from the base that's described a little bit further up in this chapter. So you know the exact memory address of this register. You can go in and print the contents of this particular register address. It'll be, if you print it in binary, it'll be a string of ones and zeros. And it tells you, bit 0 in that string of ones and zeros represents interrupt 0, which if you recall from that table that we were just looking at, that's the 0th interrupt attached to the timer peripheral. Interrupt 1 is the first interrupt attached to the timer peripheral, and so on. You can go in and just take a look at which of your interrupts are enabled. And then you can turn one on and print this contents again and confirm that, yes, indeed, I have turned on this new interrupt. So what I want to look at, though, is if we go to the ARM reference manual, which there's a link to here in just a second. Yeah, let's go to the ARM reference manual here. I want to use this to talk a little bit more about these interrupts. So we'll download it and open it. And the particular section that I want to take a look at is the exception model in these ARM processors. And what this is telling us, if we scroll down just a little bit, is that interrupts in these ARM processors appear as exceptions. They're a specific type of exception. And this table B1-3, is telling us what each of these exception numbers in the ARM corresponds to. And there's a bunch of stuff here that isn't particularly relevant to us, but that's maybe kind of interesting to look at. What I want to draw your attention to is this line 16 here, which indicates that the 0th external interrupt, so this would be interrupt 0 in that table in the RP2040 that we were just looking at. The 0th interrupt is tied to exception number 16. The first interrupt would be tied to exception number 17, 18, and so on, up to 16 plus 26. So it's these particular interrupts in the NVIC that are attached to the interrupts as described in the RP2040 data sheet. And if we scroll down just a little bit further, you could ask the question, okay, there's a particular exception handler attached to each of these exceptions. How does the processor know where the particular exception handler for a particular exception lives? There must be some sort of table where it has to go look that up. And indeed there is. There's this vector table stored in a register called VTOR, which we'll look at in just a second. This is a table of 32-bit addresses. And the 0th element in that table contains a 32-bit address that would be the entry point for exception 0 for the ARM, and so on. So if we wanted to know the address for the particular exception handler associated with, say, the 0th timer interrupt, what we would do is go down to, the 16th entry in this VTOR table, the table that's pointed to by the VTOR register. We'd look up the address at that particular index of the table. And what that would contain is the address in memory where the interrupt service routine, the exception handler for that particular interrupt lives. So let's pop back to the RP2040 data sheet for just a second. And what I want to show you is if we scroll down here just a little bit, this is the list of registers associated with the ARM Cortex M0. We scroll down just a little bit, what we will find is a register called VTOR, which we can go access. And what this does is it holds the offset address for that vector table. So if we wanted to, what we could do is go to the address that's pointed to by the VTOR register. That points to the base of this vector table. And we could print out all the addresses of all the exception handlers for each of the interrupts that we have enabled. And what we would probably see is that for most of those exceptions, they point to a place in memory that's corresponds to some sort of no exception error or something like that. But were you to write an interrupt service routine and attach it to that particular interrupt, what you would find at this table is the address in memory where that particular interrupt handler lives. So what we're going to do in just a second is go back and revisit that PWM code where we're setting up the interrupt for the pulse width modulation channel. And what we should expect to find when we dig into those C SDK functions is somewhere in there, let me just go back to that table that we were looking at. If we take a look at the NVIC table here, there's this register that's associated with setting and enabling registers. So when we dig in, somewhere in there, we're probably going to find some manipulation of this register that turns on that particular interrupt for the NVIC, right? Somewhere else in there, when we dig down, we're going to find, we should expect to find, some manipulation of the table that's pointed to by that VTOR register. So the SDK at some point is going to have to go in there and associate an address in memory, the particular address where our interrupt service routine lives in memory, with that particular exception number, right, for the ARM. So, if we were tying an interrupt service routine to the alarm 0 register, which is interrupt 0 on the RP2040, exception number 16 for the ARM, what we should expect to find when we dig in is somewhere in there, the SDK is accessing the 16th entry of the table pointed to by the VTOR register and putting a pointer to a place in memory at that particular index that points to the interrupt service routine that we created. We should expect to find that. And then the other thing that we'll find, which I haven't talked to here, is what we are doing is tying external peripherals, an external timer peripheral, an external PWM peripheral, some external piece of hardware to this nested vector interrupt controller. So in addition to all the configurations that I just talked about for setting up the NVIC, we should probably also expect to find some configurations of that particular peripheral that do things like say, hey timer peripheral, turn on your interrupt. Or hey PWM peripheral, turn on your interrupt. So we'll turn it on at the peripheral level, and then we also have to enable it at the NVIC ARM level. We should expect to see both. So let's just take a look at that quickly. So this, as I already mentioned, this is just the really simple PWM example that you started from. I'll just remind you that all that this is doing is initializing standard I/O. We're associating a particular GPIO port with its PWM function. So we're saying we're going to have this GPIO port driven by the PWM peripheral. We're accessing the slice number, the PWM slice number for that peripheral. And then this section of code here is turning on the PWM interrupt for this particular PWM slice. And sorry, I'm bouncing around just a little bit, but let me just go back one more time to the data sheet to make a point. what we are doing is turning on this particular interrupt, right? So interrupt number 4. And I want to go in and look at, we'll go down through the SDK to look at what each of these are actually doing, and then try to substantiate that with the data sheet that we just looked at. So when we're setting up this particular PWM interrupt, the first thing that we do is call an SDK function called PWM clear interrupt. What is that doing? Well, if we go to the definition of it, what we can see is it's going to the hardware struct library associated with the PWM peripheral. Remember that these hardware struct libraries, all that they're actually doing is organizing the registers, right, so that they're more easily accessed and manipulated. We're going to a particular register called INTR, and we are setting a particular bit of that INTR register. If we go to the data sheet, and let's just take a look at the PWM section of the data sheet. So we'll scroll down here to PWM, maybe in the peripherals section. PWM, list of registers. There's going to be one here called INTR somewhere. Yeah, INTR. This is allowing for us to clear the interrupt associated with the PWM channel in the event that it was set, right? So all that we're doing first of all is going in, and in the event that that particular interrupt was set, we're just going to clear it so that we can reset it. The next thing that we do in the code is we call this function called PWM set interrupt enabled, which has an argument takes the slice number. Let's go to the definition of that, and what we'll find is we are, again, accessing a particular register that's contained in the PWM hardware struct. This one's called INTE, interrupt enable. And we are setting a particular bit in that register. If we go back to the data sheet, what this is doing is enabling the PWM register, or I'm sorry, it's enabling the PWM interrupt and associating it with the particular PWM slice that we're using. Right, so in fact, in this demo, we are using GPIO 5 for PWM, which is attached to slice 2. So we're setting this particular bit of the interrupt enable register. This, incidentally, is a register associated with the PWM peripheral. So we're telling the peripheral to attach its interrupt to slice 2 of the PWM peripheral. So that line of code that we just looked at, what that's doing is telling the hardware peripheral to, first of all, turn on your interrupt and attach it to this particular slice, this particular PWM slice. The next thing that we have to do, as we just talked about, is we have to tell the NVIC, the ARM thing that's handling interrupts from the ARM's perspective, that we would also like that particular exception turned on. And we need to associate an exception handler with that exception. So let's first take a look at this SDK function here, interrupt set exclusive handler, which as an argument takes the interrupt that we're configuring and the name of the function that we would like to be the exception handler for that interrupt. So that on PWM wrap, I'll just briefly remind you, it's defined up here, right? This is just our interrupt service routine. So every time the PWM channel completes a period and throws that interrupt flag, we'll enter this interrupt service routine, which clears the interrupt. We can take a look at that in just a second, but we actually did just look at that. This is, I'll remind you, accessing that INTR register that clears an interrupt flag. So we clear the interrupt flag that was just thrown. And then, we do whatever we want to do. Maybe we change the duty cycle of the PWM wave or something, right? But this is the interrupt service routine that we want to associate with that particular interrupt. So what do we expect for this to be accessing? When we go down through the levels of abstraction of this function, ultimately it's going to be touching a register. What register do you think we're going to be touching?
The interrupt table, vector table?
Yeah, the vector table. So we'll see that in just a second. What we expect to find when we go down to sort of the lowest level of abstraction here is somewhere down there, it's going to be going to the index of the vector table associated with this particular interrupt service routine. So that's actually going to be from the base address that's pointed to by VTOR, it's going to be offset by 16 plus an additional 4, right? 16 gets us to interrupt 0 for the RP2040, the one that's tied to alarm 0, and then we have to go to element number 4 to actually access the one associated with the PWM channel. But okay, we expect for this to be going to that particular index of the table pointed to by VTOR, and to put some data at that address. In particular, it's going to put the address of this function that we want to use as the exception handler. So let's just look at that. So we can go to definition. Let's look at this. Okay, so it's doing some checks. Incidentally, you can see that one of the things that it's doing is using a spin lock to make certain that this particular manipulation of the VTOR table is not interrupted by anybody. So remember when we talked about spin locks, we talked about how not all of them are available to you because some subset is actually used by the CSDK for a variety of things. Here's an example of that. So this CSDK function under the hood, it's using an interrupt to create an atomic section of code that cannot be interrupted, where it's actually going to go in and modify the interrupt table. It's using one of the spin locks to do that. Which one's it actually using? I'm just kind of curious. So let's see. Number 9. So it's using spin lock 9 to do this, just for your information. But in any case, it goes through, and then it calls this second function called set raw interrupt handler and unlock, which as an argument takes the interrupt number and the handler and save. Can't remember what save is doing. Let's go look at this. Okay. This is calling a function called getVtable. We'll go look at this in a second, but you have a good idea of what that's doing. It is accessing element 16 plus num, 16 because the first interrupt, the one associated with alarm 0, number 0 in that table in the data sheet is at an offset of 16, plus num. How much further into that table do we have to go to actually get to the interrupt that we're trying to configure here? So that's going to be 4 in our case. But it's going to this particular index of the table pointed to by VTOR, and it is putting the address of our exception handler at that address. So let's just look at this a second. We can go a little bit deeper into here. And what we'll find is that that function getVtable, it is going to, again, it's going to that hardware structs library, and it's accessing a particular register called VTOR. Let's go all the way down the levels of abstraction here. So we can go to the definition of this hardware struct library. This is the particular field of that struct that that function is manipulating or accessing. It's going to this register, M0 plus VTOR offset, which lives at an offset of ED08 from, the base address that would be defined up here. So let's just go make sure that makes sense. So what we can now do, just to sanity check ourselves and make sure we understand what's going on, is we can go to the list of registers associated with the Cortex M0. Let's take a look at VTOR. VTOR is at an offset of ED08. Is that the same that we just saw? I think it was, right? It was at ED08. Okay. So it's going to this particular address. It's walking forward as far as it needs to walk to get to the particular element in the table that's pointed to here. that's associated with the interrupt that we care about. In this particular case, it happens to be the PWM interrupt. So it goes to that particular index of the table, and when it gets there, it puts the address of the interrupt handler that we wrote. So at this point, what this section of code is doing, we first of all go to the PWM peripheral and just clear the PWM interrupt in the event that it's set. The next thing that we do is we turn on the PWM interrupt from the PWM peripheral's perspective. So we tell the peripheral, please enable your interrupts, and in particular, please associate it with this particular slice of the PWM peripheral. So we're telling the PWM peripheral to turn on its interrupt. We now need to tell the NVIC, the nested vector interrupt controller on the ARM, to turn on its exception handler for that interrupt. We do so by calling this IRQ set exclusive handler, which as an argument takes the name of the interrupt that we are configuring. Under the hood, by the way, remember that this is just an interrupt number, right? If we go look at this, that's just 4 because it's, interrupt number 4 as specified in that table in the data sheet. So we're saying, please go to interrupt number 4 and put the address of this function there in that table. So now, when an interrupt gets thrown, that looks to the ARM like an exception. It goes to the table pointed to by VTOR to find the exception handler associated with that exception. In this particular case, this exception is at offset 16 plus 4 from the base of the table pointed to by VTOR. And it goes in there, when it looks there, it will find the address of this particular interrupt routine. And it'll go execute it. And then the last thing that we do here is we call IRQ set enabled. Let's just take a quick peek at this. What we find is oops, sorry. Go to definition. Let's look at this here. We are calling IRQ set mask enabled. Let's look what that does. And ultimately, what we find is it's first of all, clearing the interrupt in the event that it was pending, and then what it's doing is going in and modifying that M0 plus NVIC ISCR register that we talked about previously. This is the register that is from the NVIC's perspective, specifying which of the interrupts are enabled. So we are now enabling that particular register from the NVIC's perspective. So we turned it on from the PWM peripherals perspective. We turned it on from the NVIC's perspective. And then we put the address of the interrupt routine in the particular place in the VTOR table that's associated with the interrupt that we're configuring. And at that point then, the interrupt is on, right? So when the interrupt now gets thrown, what will happen is that looks like an exception. We go run, the ARM will go run the exception handler associated with that exception. We've pointed it to this function as the exception handler. The first thing that it does is clear the interrupt so that this can happen again, and then does whatever we want to do in the interrupt service routine, and so on. There are questions about this. So like I said, this conversation is at least 1, maybe 2 levels of abstraction below what is sort of probably of practical utility in the lab. But as we debug Lab 3, I want to take advantage of some of this time to remove some mystery from some of these functions that we've been using, these in particular. Okay. Is this interesting to people? I find this stuff really interesting. The next thing that I want to talk about is, okay, as I've mentioned, what we're doing in this particular line of code is we're associating the address of this function with the interrupt. We're putting an address there. Let's talk about let's go revisit the memory map for the RP2040. So what address do we expect for that to be? Or in what range of addresses do we expect for that to be? So let's just remind ourselves of this address map. What this table is telling us is which sections of memory are associated with which stuff, right? So for instance, what it's telling us is that the SRAM, right, the memory where your variables and stuff get stored, that starts at hex 2 million and extends down to hex 40 million, right? So if you declare a variable, this is an interesting experiment to do, by the way, declare a variable and print out its address, right? So you use the ampersand to access its address, and you print that address as an unsigned int and see where it lives in memory. And what you'll find if you do that for a variable is its address will start, it'll be, you know, somewhere between hex 20 million and hex 40 million because it's going into SRAM. The addresses in the range of hex 1 million to hex 20 million are associated with this thing called XIP, execute in place. The stuff stored at those memory addresses, it looks like, you know, just a place in memory. You can access it like any other memory. But when you go access stuff there, what's actually happening automatically under the hood is it's executing a QSPI transaction out to the external flash, perhaps bringing some stuff into local cache, and then, you know, accessing it or running it or whatever it's going to do. So that range of addresses is associated with the external flash where your code actually gets stored. We've talked about this a few times. When you program the RP2040 via the USB, that code goes into the external flash, and then there's a QSPI interface between the RP2040 out to that external flash so that you can execute the code that's living out in that external flash. So another interesting experiment that you can do is declare a function and go print out the address of that function. What you will find is that function's address, unless you do a sneaky trick, which I'll talk about, that function's address will be in the range of hex 1 million to hex 20 million. So that's code, so that's going to get stored elsewhere, out in the external flash. Right, and then if we scroll down, you know, this is telling you the range of addresses associated with all the peripheral stuff. So it's just kind of interesting to know. I was running an experiment this morning with this address stuff. So in particular, I added this example to the demo software if anybody wants to play with this. Let's take a look at this code here. So all that this program is doing is declaring a function called function1, declaring another function called function2 with some fancy stuff out front that I'll talk about, and declaring a variable. And then it's going through and it's printing out the address of function1, the address of function2, and the address of that variable. And what we find is precisely what we expect to actually, which is if we go in and look at those addresses, function1 is at an address that's in the range of hex 1 million to hex 20 million. Function2 is actually in the SRAM. I'll talk about that in just a second. But this prefix here, what this is telling the compiler is please actually store this bit of code in SRAM. And the variable lives at a place in memory that is between hex 20 million and hex 40 million. The variable, of course, lives in SRAM as expected. Why might this be a good trick to know? Like maybe for something like voids. Yeah.
We use it to speed up all our voids. So all of our voids had one array for x, y, position, and velocity. And so we had them all not in Flash, and then we also had some functions inline as well.
Okay. It may be the case that your code can run more quickly. if you are saving yourself the time associated with going out to doing these QSPI transactions to go fetch code for execution from external flash. You can tell the compiler here to put a particular function in SRAM as opposed to external flash. You can also, if you want to, in the CMake file, I have it commented out just for this experiment, but if you were to comment in line 20 here, Pico set binary type, with the name of the executable, followed by this no flash directive, what that says is please put this entire executable in SRAM as opposed to putting it into flash. Maybe useful, maybe not, depending on what you're doing. The next experiments that I plan to run for this, by the way, which I'll run and then I can talk about the results here in lecture, is timing how long it takes to get into an interrupt service routine and then putting that interrupt service routine in SRAM as opposed to flash and seeing if that affects the time to get in or out of that at all and to what extent. By the way, the other reason that it's good to know this sort of lower level associating an interrupt service routine with an interrupt stuff is in lab 1, you'll recall that we set up one of these repeating timer callback functions, right? Which is, deep down under the hood, it is tied to one of the alarm registers. So there is a low level interrupt associated with it, but then there's higher levels of abstraction built on top of it. So the amount of time that it takes for you to get into the callback function that you would have configured in lab 1 is significantly longer than it takes for you to get into a low-level interrupt routine associated with, say, the alarm 0 register. So if you went through a similar process here to associate an interrupt service routine with the low-level alarm register, and you timed how long does it take for me to get into that interrupt service routine as compared to the time it takes for me to get into a callback function that I set up using these higher level CSDK libraries, what you'll find is that you can get into the interrupt considerably faster. Exactly how much faster I can't remember, but it's orders of magnitude if I recall. So in some of the other examples, in particular if you look at some of the DMA examples, we go through a very similar process to associate an interrupt service routine with one of the DMA interrupts, right? So this is a particular example that uses the PWM peripheral, but this generalizes to the other interrupts on the RP2040. What do people think about this? Yeah.
Sorry, just a question from something you mentioned earlier. This is a little unrelated to what's going on now, but the executable in place, is that related to like the not the external memory like on the chip, but like if you were to use an SPI, like some sort of SPI external memory that isn't on the chip, do the addresses also have to do with that or not really?
That would be different. So what I'm talking about is, take a look up here. There's a graphic. This graphic here. This QSPI channel, this connects to an external flash memory device that is already on the Pico. If for your final projects, for some of your final projects, folks have been talking about implementing some sort of external memory device. One of these serial RAM devices, perhaps. These often are SPI devices. So you would communicate to that external memory device via probably one of these SPI peripherals. So this interface is sort of highly optimized and automatic. If you add an external memory device, you will set up the connection to it probably through one of the SPI channels. Yeah.
So when you have to access memory from the flash peripheral, does that add jitter of like, I don't know, a couple microseconds to your code?
It can affect your timing. Precisely how much I need to run the experiments to figure out. Um, One of the interesting things that can happen and that I need to experiment with is the way that this is set up. You can occasionally set up a situation where you end up with priority inversion. Folks heard of this? So priority inversion it's a situation where you have a system where you have high priority stuff and low priority stuff. So the high priority stuff is the stuff that needs to happen quickly. You need to get it done right away. And then that high priority stuff, what you would like is for it to be able to interrupt the low priority stuff so that it can enforce strict timing. And the low priority stuff, we can interrupt and get it done whenever we can, but we don't want to hold up any of the high priority things. Suppose that your code is running along and you hit a interrupt service routine that lives out here in external flash. So you need to execute one of these QSPI transactions. It can occasionally be the case that will block a high priority event from happening until that transaction is finished. So you end up with a situation where the high priority event is unable to interrupt the low priority event, and the timing of it gets influenced. It ends up taking longer than it should. There's an interesting story associated with priority inversion, one of the Mars rovers, if folks care to Google it. There are methods for mitigating this. So putting stuff in Flash can help with this. The other thing that you can do is if we take a look at, what's the section of registers that would have this? I think it would probably be the list of registers associated with the ARM-M0. Yeah. There are registers here called interrupt priority register. There's a whole sequence of them, each of which touches a different subset of the registers. So for example, NVIC IPR1, which is at that particular offset, that allows you to configure interrupts 4, 5, 6, and 7, which if we were to go look at that table, we could see, okay, which hardware are these interrupts actually tied to? And it does allow for you to assign up to 4 different priority levels to those interrupt routines. So it allows for you to, for instance, have, the interrupt associated with one of the timers interrupt the interrupt associated with some other peripheral if you care to have that happen. We haven't played with this at all in class yet because we haven't really needed to. But if you're getting really hardcore about timing, maybe this is a good thing to know about. It does allow for you to assign priority levels to your interrupt service routines.
Is code executed directly from the external flash, or does it pull it into RAM and then execute it from there?
My understanding is that it gets pulled into, sorry, it's up here. This execute in place cache. By the way, what lives in, we were looking at that address map earlier, and if you may recall that addresses 0 up to hex 1 million were associated with this ROM, read-only memory. What lives in here? This is, yeah.
Global variables and stuff like that?
It's actually like bootloader. So the code that allows for you to drag and drop the UF2 file onto the Pico and it just sort of gets automatically loaded up. There's a bootloader required in order to make that happen. That bootloader lives here in ROM. Fascinatingly, it's open sourced. You can go to GitHub and look at the code that actually lives here in ROM. But probably it's the case that you aren't manipulating this. This is static and it is in place when you buy the chip from the manufacturer. The code lives there already. Okay. So I think next time we'll talk about music synthesis, because I think that's going to be relevant to a pretty wide variety of groups. I want to talk about low power. And then we'll take it from there. Right? We'll keep talking about stuff for as long as it remains useful to you all, and then as soon as it's not as useful anymore, we'll transition to more lab time. Okay, thank you all.